lot of data. I hope online people are able to hear me. You can give the feedback to the organizers. Asana will take. If there is any difficulty in transmission, you please get in touch with her. So these are all the various operations that we can do with light. So many of them are very dramatic. Display. See, all these are actually optical display we are using. But at the back end is all electronics. I have not put one important information operation that we do often. That is memory. Storage is an important aspect of our communication systems and information systems. So there's a lot of scope for optical information, storage, processing, and all those things in practice. So if you want to go fundamental differences between electronics and photonics, we have to go back to their statistics. Many of you know that in semiconductors, we use Fermi-Dirac statistics to study all the device properties and characteristics. So similarly, as a contrast, we use Bose-Einstein statistics for the statistics of light. And of course, you have others, macroscopic properties like mass. Photons have zero rest mass. So that means their momentum can be very high compared to electrons. Similarly, there is no charge on the photons. So it's difficult to control compared to electrons. These are all the various comparative plus and minus points of electrons and photons. Now, we need not go too deep into photonics right now, but only I would like to once again mention that since about 1960 or so, you can say is the era of modern optics. When the laser was invented, after that, a lot of applications have come. Of course, there were earlier many applications, but a lot of changes have taken place due to the invention of a laser, including optical communication. So I would like to now touch upon what is this integrated optics. You can compare integrated optics to integrated electronics. In olden days, during 80s or so, in electronic circuits, we used to do on a breadboard or a PCB, and then put many components and make the system. Of course, now you know that it has translated into what you call it as VLSI. Present day, all our electronics has taken over into VLSI. A very small chip, like Intel chip or so. If you see, millions of transistors, including memories, so many things are put on that. Logic gates, so many things. So integrated optics can be taken as analogous to integrated electronics. Very primitive stage. We are in a very primitive stage. What can be made on the chip in optics. But there are very good indicators that it will be very advantageous. Some things which you have been doing with millions of transistors, you may do with a few optical components. The best example is the Fourier transform. For most of the image processing, we have to do the Fourier transform of the image of the object. So in electronics, what you do, with a CCD camera or so, you capture the image, big lot of data, so many MB, and you do lot of processing, electronic processing to get the Fourier transform of that. Whereas most of us know that in optics, if you put a lens in front of the object, you can do the Fourier transform. All points on the object simultaneously on the back focal plane of the lens in a one shot, in one clock cycle, if you want to talk in terms of clock cycles. So that is the what is called functional approach to these problems. So we need not follow exactly what we do in electronics. So we can do a functional approach to optics. So in that sense, lot of devices. For example, in the earlier case, in the case of image processing, we can make a lens on a chip. If you make a lens on a chip, then we can integrate all these operations on the chip. So there are many examples like that. People have developed switch arrays. If you want to do optical networking, people have done N by N switch arrays are available now, commercially also. Then in our lab, we have done what is called this fiber optic gyroscope. There's a chip for fiber optic gyroscope that we did. I will show you one slide later on towards the end. Then, at the beginning of the century, people have started talking about MEMS. MEMS means micro electromechanical systems. You can integrate mechanical components, electronic components, optical components, all on a small chip. That's a positive. I'll show you one slide of that also. So these are all the various aspects of integrated optics. That means there is imitation from electronics, there is imitation from bulk optics. There are certain very unique features which are not available in electronics or bulk optics that are possible in when you go onto the chip. One example I would like to give. This is the optical modulator on lithium niobate. Lithium niobate is a crystal which has got electro-optic properties. That means you can change the refractive index by applying voltages. What you see is the interferometer, Mach Zehnder interferometer. So there is a input branching arm. Then there are two arms of the interferometer. Bluish ones are the electrodes which are put on top of that, and then a combiner. So if you launch light into the input, it splits into two arms, and then when we apply voltages, the relative phase difference between the arms is reflected at the output end. So you have a phase modulation due to this electro-optic effect, and which is converted into amplitude modulation by this MZA. So there are very good features of such a modulator. In the present day practice, many of the high-speed modulators are this type. And lithium niobate has become very popular material. Of course, it's not the most suitable material, but at the present juncture, lithium niobate is a very good material. And of course, still for people who want to do research and to invent newer devices, etc., you can definitely experiment on the lithium niobate later on in the future. If you look into the future, we need to have active materials like this, like indium phosphide also. So these ideas can be translated into more active materials in future. Presently, as you can observe, silicon is the most popular material for most of the electronics, even photonics applications. A lot of photonic devices can be done on silicon also. Not very active devices, but most of the passive devices and the electronically controlled devices can be done in silicon. So this particular modulator can go up to say 100 Gbps also easily. Whereas you cannot go by direct modulation of a symmetric laser. You cannot go for 100 Gbps up to maybe 5-10 Gbps you can easily go, but not beyond that. That is the advantage of external. This is called external modulator. You have to launch the laser light into the input arm and then detect it at the output. Of course, all this will be also combined on a PCB later on. It's a hybrid integration. You cannot say full integration, but it's a hybrid integration. One more important device in integrated optics is called the directional coupler. There are two waveguides placed very close together, what you see here. These are all top view I am showing you. Two waveguides are very close together. And once again, I use electrodes to manipulate the properties. So when waveguides are very close together, light can tunnel from one port to the other port. One arm of the interferometer, one arm of the directional coupler to the other arm, you can tunnel. Just without doing any electro-optic also. So we can work out the mathematics of that. To take the wave equation and apply, then you can see that all the light from the input port can be pushed onto the output port. Crossover state. You call it crossover state. Then you can also apply the voltages on these arms and then change the properties. When we change the refractive index, it is possible to design such that once again crossover takes place from the second port to the second port, first port. So the light comes back into the second port and goes back. So you can have a bar state. When there is voltage, you can get a bar state of the switch, and when there is no voltage, you can get crossover. Just imagine two signals, S1 and S2, optical signals, and they can go into bar state or a crossover state by using this. There are many advantages or many applications of this. For example, you can make logic gates, AND gate, NOR gate, etc. You can make couplers, 3 dB couplers. Suppose you want to make, it is purely passive. You need not apply voltage also. So you can easily design half this length. This is a 3 dB coupler. Similarly, phase shifting can be done. So many things can be done with this. Time delay you can achieve. Earlier I said memory is difficult. So you can delay the light to a certain extent and use it as a memory element. Suppose you want a correlation between the first port and the second port with some phase difference. You can do it by this method. Little bit of fabrication details here. So this lithium niobate, usually you diffuse titanium into that. These are all titanium diffused lithium niobate. You can make waveguides by diffusing titanium. It will increase the refractive index a little bit. 1% change in the refractive index is also sufficient for making good waveguides. Then a few volts is sufficient to change the electrode voltage. About less than 10 volts is more than sufficient. And then this fabrication is slightly, you have to do in a controlled environment. In this particular, typically we used to do for about 8 hours diffusion into this of about a few 100 angstroms of titanium strip at 1000 degrees centigrade. This is one example. There are a lot of other technologies, easier technologies. For example, if you want to do passive devices, you can do on glass. You can do proton exchange on glass. It takes about 20 minutes or so to make a good optical waveguides in glass. These are all some of the standard features of photonic integrated circuits. Most of them are based on the single mode operation. That's the most important feature. Many of you know that the fiber optics goes on in single mode. All the fibers that we see around are all single mode. They avoid dispersion. Here it is not that dispersion is our main problem in integrated optics. But design is very convenient, and also the devices are very compact, very small. Typically 4 microns is the width of the waveguides that you see around. Fiber optics, you know, about 9 microns. And you can also manipulate the modes, because most of you are from the physics background. You can calculate all the modes of these optical waveguides and then manipulate. Suppose there are 4 modes in a waveguide. You can exchange power between them. You can redistribute, so on and so forth. I would just like to mention in one of our recent research, we have made a few mode waveguides for quantum applications. In quantum, what you do is you want to have a different energy states, or states, not just energy states, different states. You can call it qubit states, state 1, 2, 3, 4, etc. So generally you use energy levels as the states. We can also use modes as a state. Mode 1 is 1 qubit state. Mode 2 is another qubit state, and so on, and then you can manipulate. This is called higher dimensional qubit operations. That's one of our recent research. I think I have not put anything about the quantum in this. So the other important advantages of the integration are due to lithography. See, most of these we use lithography to fabricate. So automatically they are aligned. Suppose you want to make a modulator and a phase shifter or a coupler, by lithography they are aligned. You need not adjust separately, except for the source and detector. Of course, source and detector also well packaged nowadays. You can put in some V grooves and then package this chip very well. You can also control these light waves that are propagating in the waveguides. You have just seen the modulator. You can manipulate the light. Suppose you want to make a 90 degrees bend. You can make a pattern in that shape. If you have Y branch, I'll show you one or two. If you make a Y branch branching circuit, power is automatically divided. So you need not, you see earlier in olden days, or even in fiber optics, if you want to divide the power, you have to adjust carefully. That problem is not there. Then, because these are all small, the application of voltages is very small. You don't need very large voltages. This can be compared with a bulk electro-optic device. Suppose there is a ground plane and on top of it you put electrodes. The thickness is more than 200 microns. Typically, all these wafers come with 250 microns or so. So there is a very large gap. So you have to apply a lot of voltage. People used to apply 100 volts to get the same modulation. So now we can get with very small power levels. And also the speeds are also very fast because see, I'm looking both from electronics and optics point of view. So the electrode voltages are very close. The electrodes are very close, a few microns once again. Then the capacitive effects are very, very small. So they will be very fast. And also many of you know about the power densities in an optical fiber. If it is 9 micron and the fraction of a milliwatt of power if you are transmitting, intensity is very, very high. You can say typically some rules of some calculation will show that it is about 500 times the sunlight. So daylight, if you take it, you feel that it is very intense. So the light going in an optical fiber is very intense compared to daylight also. So a caution from the laser safety people is that you should never operate without goggles. And also even the reflected light falling onto your eyes or skin is not good. So from scientific point of view, the high density is very important for many, many applications. For example, you can make nonlinear effects. You can observe a lot of nonlinear effects with high power densities. So if you want to observe second harmonic generation or a four-way mixing, etc., you can do it very well in integrated optics and also fiber optics, of course. But fiber optics, the negative point is fully passive. You cannot do anything once the light goes in that. You cannot manipulate. Of course, like in VLSI, these are all very compact, lightweight. These are all the features of photonic integrated circuits. Very briefly, a little bit of history. You can start with modern optics. You said 1960 is when the laser is invented. So immediately after that, people have worked on optical waveguides. Many dielectric media people have explored like glass, crystals, and so on. And a lot of all this waveguide theory has developed during the 60s, you can say. Then during the 70s is the era of semiconductors. A lot of optoelectronic devices have been miniaturized, like photodetectors, LEDs, laser diodes. Many laser diode arrays also have been made, which have become very, very convenient for optical communication applications. Even if you want to have large power, you can make many laser diodes and then you can combine them. Of course, much of the optical communication is not coherent. You don't need coherent light for that. But laser light is definitely advantageous for various reasons, not only coherence. Intensity is good. Then all the other noise-related properties are good, etc. So during 1980s, this is the era of applications. Many people have built fiber optic communication links all over the world. That's what is the big push for all these subsystems and optical systems. As you know, in 1990s, it is the era of internet. Internet has started, email and all these things and people thought that we will do networking. Local area networks have started. Instead of only point-to-point communication. You see, if you observe present-day world also, the big optical communication links are all point-to-point between different cities and so on. And there is also this national backbone network. That's also networking all these, even up to village level, by fiber optics. But all these are point-to-point links, interconnected with electronics. They convert all the signals to electrical domain, extract the signals and retransfer. That's what is happening in all the links that we see now. It's not fully optical. But there are certain links that in some big companies and some campuses, you have fiber optic LANs. You need not convert them into electrical domain. That means the bandwidth is not lost. What is the advantage of being optical? Fully 5 Gbps or 10 Gbps at once. And also there are other new things actually I have put there. People have thought about what is called this WDM, wavelength division multiplexing. You can assign one wavelength to each user. They communicate on their own wavelength. And when it comes to the detector, they will tune according to the wavelength. So wavelength has become an IP address. Nowadays we use all your IP address. Is it not? For all the internet applications, we use IP address. So in a small, you see, it's not a big LAN. Smaller, say some 100 wavelengths or so LAN, 100 IP addresses it can. Because what people do then is they will do subnets. Some 50 or 100 people in one subnet, 50 or 100 people in another subnet, and then communication between them and all that. That is it, management, optical network management they call. Then in the recent times, people are trying to push it more and more optical. As much of electronics as possible to replace. But I have not written here the most important development in the recent times, not recent times, the beginning of the century is the MEMS. People are trying to integrate optical devices along with the MEMS. In the recent times, last 10 years or so, there's not too great a development in electronic hardware. See, if you look at Intel chip or something, or the laptops, the speeds have almost saturated. And different optical applications have come into force. In the last 10 years, you can say the quantum is a big buzzword. Many people want to do quantum computing, quantum communication, and so on. But the technology is not ready. They use electronic systems, atomic systems, nuclear systems. These are the possible candidates for quantum applications. So they are not able to go big way. Suppose I want to have a 16-bit quantum computer. It's difficult. A lot of difficulties are there. If there is a good, I would suggest you have a good quantum workshop under your optical chapter. Then people can discuss various things. So there is the, I mean, I just mentioned there is a problem of decoherence. If you are talking about more and more objects, many photons, more than one, even single photon, gradually its properties will deteriorate. It will not be coherent. So that's an important problem that has to be tackled in quantum. So those are all different problems. We'll not worry about those. But I would like to say in the development of photonics, presently we are at the state of a quantum. Then a lot of applications of optics. Fiber optics is well established, we'll let us assume. Then a lot of scope for fiber optic sensors. Lot of sensors are getting converted into fiber optics. And integrated optics will play a role for miniaturizing them and to do little bit of signal processing you can do, optical signal processing you can do on the chip. These are all the possibilities. But still we are nowhere closer to VLSI. In fact, VLSI people also talk about silicon photonics. See, they say that the VLSI is getting saturated by quantum limits. So we have to go for what is called the silicon photonics. They have, many people have started communicating or interlinking the processors with optical links, both free space links on the chip as well as optical waveguide links. These are all the things that are coming up, what they call silicon photonics. These are all the developments in the historical scheme of things. Let me just quickly show you some devices. So I'll show you some, see, optical waveguides are the basic devices you can see, like interconnects in electronics. Like wires, you can use optical waveguides as interconnecting elements between different components, like a modulator and a switch. Then a lot of passive waveguide components can be made, like tapers, branches, and so on and so forth. Then the dynamic effects like electro-optic effect can be used to make modulators, switches, and so on. Other keywords there are thermo-optic, magneto-optic, opto-optic, nonlinear optical effects. These are all available in many material systems. Like for example, lithium niobate itself is a very good magneto-optic or non-linear optical material. So we can make use of these. Of course, there are good candidates for each of these effects. Then, of course, we are not discarding electronics. Electronics is very good in terms of control, we said, is it not? So you can, electronic control of optical devices is possible. So for example, in semiconductors, you can control the junction characteristics or the mobility of the charges, etc. And then light matter interactions will be very, very useful devices. That's one of the active areas of research that goes on right now. Then finally, when it comes to practice, the technology is going to be important. The materials choice, the fabrication techniques. Many of them we are adapting from electronics right now, but in future, definitely yes, we should be able to come up with new methods, techniques for optical fabrication. So these are some of the waveguides. Cross sections I am showing you all the cross sections. So there are buried type of waveguides. You can deposit a small strip on the top of a substrate and diffuse to get this first buried type of optical waveguides. When you can just imagine the refractive index in the guiding region should be more than that of the outside. See, in this case, substrate is there, air is there, and then NF refractive index of the film, which can be slightly larger. Similarly, you can make ridge waveguides. You put a uniformly some medium and then etch out all the unnecessary regions. Then you get a ridge waveguide. Similarly, you can also make a loaded waveguides. You put a strip of metal and apply voltage on that, and the refractive index below changes, and you can make loaded waveguides, what they call. Similarly, you can also make induced waveguides. You can induce waveguiding effect, like in lithium battery we saw just now. So this is a broad summary of the technological issues. There are various material systems like polymers people have been using. Glass is of course popular for passive devices. Then you have sulfides, the lithium niobate, then magnetic materials. If you want to use polarization dependent properties, these are all the various systems. And I would like to say nitride is a very popular material now, presently in VLSI. A lot of CMOS technologies, they are going instead of oxide, you put additional layers of nitride. So as you know, nitride will have slightly higher refractive index than oxide, and so you can make very small and very strong waveguiding devices. Then depending on the, of course, into the future, I mentioned that we should go to active materials like 3,5, indium phosphide, gallium arsenide, aluminum, indium arsenide, and these combinations will be going to be an important material systems for photonics. There are labs, you see, of course, maybe towards the end we'll discuss about professional issues. There are labs all over the world now gradually setting up 3,5 systems. In India, not yet well, but of course, one positive thing for India is a lot of semiconductor companies are coming out into India. So there's a good possibility that these people will get on into the photonics. So there will be much more scope than what we have been seeing right now. So depending on the material system, you have to choose their fabrication techniques. On the left-hand side, all these are mentioned, a few, not all. So a lot of deposition techniques are already available in VLSI. Then you have, for semiconductors, you have growth epitaxial techniques. So corresponding to this, you can choose. And I have circled them so that you will know something which is well developed, something which is very primitive, etc. So you need not for the time being worry too much about the technological issues. If there is I suppose you have some good courses on photonics, then you can go deeper into those. So I'll show you some passive devices like couplers, dividers, polarizers, mux, demux, gratings, lenses. All these can be done on the chip, and people have done that. So this is a top view of some power dividers. By lithography, you make patterns like this and diffuse, you get these devices. So you can launch light into this and get power divided. Similarly, you can cap a small portion depending on this angle. You can get a small fraction at the output port W2. Similarly, you can make 1 by 3. You can cascade 1 by 2 into several pieces. So it appears very straightforward, simple as functionally, but the design or the functioning is quite involved. I will highlight 1 or 2 points. There is a corner here, sharp edge. It's not very good for optics. The mode propagating will be distracted by that, you can say. And also, you can also see a taper. Here the width is W and here the width is 2W. So if you are propagating a mode, it is depending on your design, it can become 2 modes. Sometimes you can use it for advantage also. So these are all the things. So directional coupler we talked about. You can have different types of directional couplers. In the second one, the waveguide arms are joined. There's no gap. That means double the width. Okay. And then you have a 3 waveguide coupler. You can make 3 or more waveguides together. You can couple light from across all these. So you can invent your own function. What do you want to use this for? Star couplers are needed in many optical networking applications. You launch light into one of the ports, it has to be divided equal among all the output ports. Because for the time being, we are not so much worried about the mode properties or coherence properties and so on. But simply if you want to divide the power across different ports, it is possible to use such a very crude type of mode mixing. The second one is a reflecting type. Light will be reflected from this edge. Actually, not a mirror, but you cleave the edge such that it is perfectly reflecting. And so you can get redistribution. The challenge here in all these, both these problems are to distribute the power equally. It's not possible. You see, from geometrical optics or from lens design type of tools, you can work out. Generally, it is not easy to get equal division, but it is possible. So polarization is an important problem. You want to make polarizers. See, I would like all these things you compare with your bulk devices. Suppose power divider, beam splitter you use, for example, in optics. So that can be very small, like this Y branch. So for polarization, you have to use what is called these anisotropic properties. You quote a anisotropic medium on your whatever conventional integrated optical circuit, or you can make the devices themselves on the anisotropic crystals, like lithium niobate. If you make, it has got a different ordinary index and a different extraordinary index. So the propagation is different in different directions. You can use that to make polarizers. Anisotropy is a very good way because you can put one more layer on top of that and then the same circuit you can use. So you can also control the polarization. You apply some other extra voltages or rotate the polarization state. All these things can be done on the chip. Mux demuxes are needed in systems like WDM. You want to combine many signals into a one single port, or you want to separate out. Let us assume there are 4 wavelengths coming from this optical fiber: lambda 1, lambda 2, lambda 3, and lambda 4. 4 different signals of different wavelengths, each one carrying different data. How do you separate them out? It's an important problem. In this case, I'm showing these lines like things are gratings, periodic variation. I'll show you in the next slide. So this grating can deflect the light in some direction. Then all other wavelengths are passed through. Then the second one will deflect the lambda 2. Third one will deflect lambda 3. So like that you can separate out all these 4 channels. Instead of transmission mode, you can use reflection mode of these gratings also, and then you can tap all the signals that are coming. You can also do the reciprocal operation. The signals are coming from different ports, you can combine into one single port. Lenses also can be made, people have made. So different types of lenses, geodesic lenses, then gradient index lenses, thickness type of lenses, all those things are made. In a simple case, you can say this is a refractive index varies like this. Maximum refractive index here and smaller refractive index outside. Like the sin x by x pattern you remember, is it not? In optics, that's a very common thing. So if a broadband or a spread light is falling on this grating, it can focus at a particular point. Similarly, you can make the thickness vary because it is more advantageous because the refractive index is same, but the thickness is different. So this is the gradient index, gradient thickness lens. So gratings are one of the most multi-purpose components in optics. You can do many things for that. For example, one of the important problems we face is how do you launch light into the chip from outside? From a fiber optic or from a free space laser, you want to launch light into this chip. So the most common method now is called the grating couplers. Almost all of the world now they are using that. In packaging also they package fibers appropriately, they cut at a particular angle and then they package. You can also use gratings to couple different waveguides. Earlier in the directional coupler, only gap was there. Now I make a grating in between the gap, then it will couple very well in a very short distance. See, earlier one what I showed, the directional coupler is very long. Typically, is the orders of hundreds of microns, say some 200 micron. See, I said waveguide gap is only some 4 or 5 microns. Length is 200 microns. That is very long. The silicon people are not happy with that. See, the silicon, these VLSI people, they want square type of devices. Like Intel chip, if you see, it is a square. You can use all the space very optimally. Whereas if I want to have a small directional coupler from this end to that end, suppose you take this as the chip, from this end to that end is the um, coupler length, and width is only small, this blackish region. Thin and long, aspect ratio is very long. So we cannot make, particularly if you want to cascade, it will require a lot more length. So silicon people are not happy. So in that, what is the solution? You can use gratings to shrink. The other techniques are there, like you can use resonators, you can use photonic band gap structures. These are all the various ways in which you can compress or make smaller devices. Then people have made in lasers, you use gratings as a reflectors. On the both sides, you put gratings, they will act as a resonator. Similarly, you can convert mode. Suppose if the waveguide supports more than one mode, from first mode to second mode, you can convert using this grating, which is printed on the top. And you can do filtering, mux demuxing, many operations you can do with gratings. So this is one of the commercial example called AWG, arrayed waveguide grating. The crux of the, you see, the function is like this. There are many input ports, there are many output ports. Light can be there in one or more of these, and you want to shuffle. You want to make a matrix of connectivity. That is the function. The crux of the problem is this delay lines. These are called waveguides of different length. So there is a different phase shift in each of these. And then when they combine in this mixing portion, or at the end, by the end of this mixing portion, the maximum will be only at that particular port. For example, blue is shown to be maximum here. Orange is shown to be maximum here. So this delay lines are dependent on the wavelength. The phase shift is dependent on the wavelength. This input section is for the mixing. It will say, for example, if light is coming from one of the ports, it will spread across all the delay lines, delay elements. So this is like antenna arrays. If someone has studied antennas, you can give progressive phase shift to each of, suppose there are n number of antennas, and each one is given a different phase shift. They will point in different directions. If you want to point in 30 degrees, there is some phase shift. For 45 degrees, another phase shift. Similarly, the AWG is doing such a function. The lengths of arcs are chosen such that they give us specific phase shift. That is the idea behind that. Because it's a very cool picture, people have made it very compact now. Large number of ports, not only 8 ports, people have made 64 ports, 128 ports, and so on. Big matrices. We can also do computing. So when people are talking about optical computing, you can do matrix operations, and also you can control these lengths if you do on active materials. All these things are possible with AWGs. I'll show you a few dynamic devices. These are based on all these effects: thermo-optic effect, electro-optic effect, magneto-optic effect, and so on. So we have to introduce that effect. So this is an example of very simple, crude example of a thermo-optic device. You have an interferometer, and the arms of the interferometer have heating electrodes. You heat the device, heat the waveguide to change the refractive index. So you can make on-off switches and so on. Some parameters are given here. Potassium ion exchange is used. That's what is shown here. This is one of the technologies. Because I'm not showing you too much about technology, some information is put there. Similarly, dimensions. This is very long. 5 millimeters is there, the length of the arm. So it is at a laboratory level, it's very useful. And now not only laboratory level, in practice also, if you're not talking about very big VLSI, you can easily use this. See, compare this with the mechanical things that we have been doing. How to adjust it manually or mechanically, it's very difficult. Thermoptically, it is smaller. Of course, it's not high speed. Thermal effects are somewhat slow. So these are electro-optic models we have talked about earlier. I would like to highlight one point here. You can. This is a top view, and you have electrodes and all that. Here you see that the electrode is a spread. It's not a lumped electrode. See, when you are talking about high-speed operation like 10 gigahertz, then what happens? These electrodes will not act just like lumped electrodes. They will act as a traveling wave electrodes. Like in microwaves, you have coplanar lines, strip lines, and so on, is it not? So similarly, the microwave will propagate on those. That means at some points the electric field intensity is more, sometimes low, and so on, some pattern. So it's a traveling wave. Microwave is traveling on these electrodes. You have to have a matched load, and so on. All these microwave IC related techniques you should use. But the main point here is microwave is traveling on this, light wave is traveling in the optical waveguides. So the velocities are different. The medium properties, dielectric properties for microwave frequencies and optical frequencies are different. There's a mismatch in the velocities. So all those can be used to make very high speed modulators. People have gone up to several hundreds of gigahertz modulators using such techniques. And some of them are available commercially also. If you look at any techno-commercial magazines, I suppose in your college also you get photonic spectra, laser focus world. I hope you get all those, is it not? They are free. You can subscribe from your Optica chapter also. That is not Optica, but they are available freely. Biomedical optics, but all is available freely from either HODs or even students' name, or you can register and then you can get the one copy. You can get free for the department. Everyone can subscribe electronic. You don't need to do a physical one. Let us get going. Switches we have already seen, there are a lot of configurations. You can manipulate with the electrodes so that you get best performance. So acoustoptic effect means the refractive index of the substrate or the waveguide changes with application of stress signals. Stress signals, not purely sound waves. Of course, sound waves also are stress variations in the medium. But here you are talking about a high speed, I mean, low wavelengths, you can say, sound waves, ultrasonics, let us say. So you have an interdigitated pattern like this, positive and negative voltages alternate. So if you apply voltage to this, what happens? If this is a active medium, you can create plus and minus refractive index. Refractive index is varying periodically. At some point it is high, at some point it is low, at some point it is high, some other point it is low. That means you are creating a grating along the length of the propagation. In conventional gratings, you have a grating like this, you pass light through this, and lines are in this direction, and the diffraction is going on in the other direction. Now, in this case, in the propagation direction, you have variation of refractive index. This is similar to FBGs. Someone, if they are studying fiber Bragg gratings, here also you have refractive index variation along the direction of propagation. You can make by using a phase mask technique or something, you can easily make FBGs. FBGs are commercially available also now. You can, if you are working on fiber optic sensor, you can just buy those and then build sensors and systems. Here I am showing you that you can make gratings on the chip, and acoustoptic effect is a very effective way to do that. In fact, if you change the voltage, then you have a different grating. Here what I am showing is this black patch is such an IDT pattern. You apply RF to this, change the RF. Microwave stage, for example, 3 gigahertz signal or 100 or 500 megahertz signal, you can apply to this and change these grating properties. So what this grating is doing, it is deflecting light in different directions. So if you change the frequency, it will deflect in a different direction. You can scan the beam by using this acoustoptic effect. And also you can do a lot of manipulation. For example, you can modulate the light beam, you can modulate the RF, and so on. So you can do computing also. For example, if you want to correlate the signal S1 on the light beam and signal S2 on the RF beam, you can get a correlated signal at the output. So signal processing can be done by using acoustoptic effect. One more, magneto-optic. If you want to make magneto-optic devices, we have to manipulate the polarization state. So the magnetic materials are most suitable there. That means there is you have to coat. Earlier I said anisotropic. You have to put a magnetic medium on top of these crystals. Then you can manipulate. And magneto-optic means your magnetic field will influence the refractive index. Non-linear optics, not much detail. I am showing you an example of a second harmonic generation. If you change the intensity of light propagating the wave, suppose you launch a higher intensity light beam, then it will induce nonlinear effects and you can get all the corresponding results. Like in this case, we are showing second harmonic wave at 420 nanometers. Input is 840 nanometers, output you are getting 420 nanometers. There are a lot of other difficulties I'm not highlighting. For example, you should do phase matching between the second harmonic signal and the primary signal. I'll show you one or few systems. So this is an example of a very simple, let's say, example. It's very easy to appreciate. No need of big physics or principles in this. So here what I have 5 switches, S1, S2, S3, S4, connected in this form. And then 4 input ports are there and 4 output ports. So you can launch signal from any of these ports and you can get at any of the other output ports. You can also excite simultaneously all these 4 ports and get a different combination at the output. So you can work out that matrix, connectivity matrix, you can work out what are possible, what is not possible. All are not possible. All combinations are not possible. How do we get? It's an important question. You can play around with this connectivity, these switches, and then you get a different output combination. So information processing can be done, like what I mentioned earlier. You can do information processing using optics. Here what I'm showing is called a spectrum analyzer. You have a laser bringing in the light in. RF is some outside source which has whose spectrum we want to analyze. And there are 2 lenses, geodesic lenses are printed here. So this RF is given to the IDT pattern and it creates a grating in this region, which will split the incoming light. But here there is a composite RF signal, not a single frequency. So it's a complex grating. Not some pattern is there for refractive rate variation. So correspondingly, you get the spectrum at the photodetector array. There are n number of photodetectors, each one corresponding to a different spike, and you can get a very good spectrum analysis. People have also done optical spectrum analysis using this. You fix the RF, whereas the signal is there on the optical. So you can do optical spectrum analyzer also. Nowadays, many of you know that spectrum analyzer is commercially also available, mainly by using gratings. Fiber FPGs people used to make this. Conventionally, people used to use some lenses and components to make a spectrum analyzer. That is somewhat bulky. Fiber optics is slightly smaller, it can come in a small box. This can be on the chip, you can do spectrum analysis. So this is an example of a sensor application for sensor, not exactly sensor. Okay. So this is a fiber optic gyroscope, has got a coil of optical fiber. Many rounds, not a single one round. So you launch light into the forward direction and also into the backward direction. So the interference of these 2 will give a phase shift. See here, you can see here, one signal in the clockwise direction, another light in the anti-clockwise direction, the fiber coil. And this is combining and splitting. So what happens, delta, not this delta phi, the phase shift in the coil, suppose you put this gyroscope on some missile or aircraft or something, and if it is rotating, there's a phase difference between these forward and backward waves, which is proportional to the angular velocity. So phase shift proportional to angular velocity. You can make a fiber optic. That is the idea behind. This is called a Sagnac interferometer compared to your MZI Michelson interferometer. This is called a Sagnac interferometer, and you can get a very good phase shift, very good rotation dependence. So in order to do that, you have to have all this circuitry. Like you must work on single mode waveguides. You must have a polarizer, 3 dB coupler is there here, and a phase shifter is there here. All these things are needed. This we can put on a small chip. In the earlier days, people used to use discrete components and then put it inside in between the coil. Suppose you wind the coil around a tiffin box size coil. In between, they used to put all these things. Now that is also reduced, and you can put all this in an integrated optic chip. This is one of the project we did in our lab long ago when my professor was there. He has taken a project from the defense labs to do this. Of course, at that time they did fiber optic gyroscope. Dr. Abhilash was there at that time, is it not? In our lab. You were there? Dr. Abhilash is there here. I think you were there at that time. When we did this fiber optic gyroscope, you were there, I think, in our lab. Yes. So later on, when I became faculty, we took up this gyroscope chip. Earlier, Dr. Jagannath Naik was there in our lab. He's the one who has done this fiber optic gyroscope. He's from RCA Hyderabad. He has done this as his master's thesis. Then later on, he has gone back to RCA, and then it took long time. It's not simply just like talking like this. See, principle is very easy to describe or mathematics to solve to some extent, I mean. But they took about 10 years to realize this. And this is going into many of our systems, like in Agni, Nag, Prithvi. They use this gyroscope. They are making themselves. In fact, earlier they used to buy it from Russians. So later on, after Kargil war, they have not given us these lithium niobate chips and all those things. So they have to make themselves. So this is another example. Japanese are very, very fond of this high-speed discs. Lot of memory they want to put. This one nowadays not much progress in this direction. At that time, they made an optical disc with very, very small pits, and in order to read and write onto that, they made this integrated optic chip. So you see a grating here. This is Fresnel grating sort of thing, and then the different electronics to address these and all that. By the way, all these pictures are the standard material until now. I've taken from Nishihara's book. If someone is taking the course, that is a standard book for that. Of course, now a lot of other books have come. All the waveguide theory, then theory of these couplers, little bit of support technology, all are there in that book for those who want to go further. Now, a few slides I will use to show you recent developments. So these are called ring resonators. If you want to make more compact photonic integrated circuits, you have to use ring resonators. Many of them are from the literature. You can see that fabricated rings. You can make waveguide in the form of a ring, and the middle one will show you the simulation of that. One plus point presently, not in the earlier times, is a lot of simulators are available now. You need not solve all those Maxwell's equations or wave equation, etc. But you can, the drop down will be there. You choose a device and it can simulate all the waveguide modes, propagation characteristics, and so on. So you can easily solve all this without, of course, it is better to know the mathematics behind that. Particularly if someone wants to do research or do a good project, then definitely you will need to have a little bit of mathematics. So you can make a lot of ring resonators for many applications. You can use the ring resonator as a filter. You can use it for logic gates, many things. So these are all the various applications of the ring resonator. A little bit of mathematics, you need to worry right now. See, the spectrum is important. The ring resonator spectrum is like this. And if you change the parameters, like the radius, then it will shift. Like in FBGs, you can use this to shift. And then you can make sensors or filters or whatever you like. Mathematics is not difficult of ring resonator, except that wave theory, if you want to go, it is not easy. Okay? Because earlier, I'll show you just a highlight, one point. See, there is a bus waveguide and a ring. The coupling is there from bus waveguide to the ring. Waveguides are not parallel. The ring is a curve and this is straight. So the coupling is variable. That's where you get into, see that directional coupler will need to solve systems of differential equations. So for the ring resonator, the coefficients are variables. You have a differential equation with variable coefficients. So that is a very good opportunity for those who want to do research or those who want to publish. So then I'll go to another application. This is called photonic bandgap structures. This is one of the hot topic recently. You have, this is a top view. On a silicon wafer, you can make holes like this. And then when you launch light into this, you get a like electronic semiconductor crystals. There is a bandgap structure. Like valence bands, conduction bands, you have certain regions where light can propagate, where light cannot propagate on some frequencies, and so on. So there are complementary type of structures. Like this is a square lattice, what I'm showing you. Similarly, this is a triangular or hexagonal lattice. So a lot of possibilities are there, like in semiconductors. The first one is called a 1D. This is simply a grating. It will act as a mirror and so on. So I'll show you some examples. So this is the spectrum. Nowadays, very good software tools are there. I will mention about MPB, the Mighty Photonic Band Gap tool. You can download that. MIT people have developed for electromagnetic emulation. Similarly, MEEP. MEEP does FDTD. So these are all based on FEM, FDTD, and all these numerical techniques. So you can just download them and then you can launch and then choose the structure and then simulate. Many people are doing that. For learning, it is good, okay, to introduce a course in a classwork or when the new students come to join for research, etc. is a very good way to get into the subject quickly by using the software tools. But after some time, you have to solve your own problem with all the equations and all that. A lot of design thinking is necessary for this. So this spectrum is dependent on many parameters like the lattice constant, what is it, refractive index variations, polarization of the light, all those things. So I'll show you one application with this, which we have done in our lab. This is a 4-channel comb filter. So how to use this is an important question. The photonic band gap is used based on defects. This is called a line defect. One complete row of holes is removed. That will act as a waveguide, very compact waveguide. Similarly, a point defect, the point C's are point defects. You can choose the point defect such that it will respond to different frequencies. So I have chosen C1 to respond to lambda 1, C2 to resonate at lambda 2, and so on. And then the other thing is waveguide. And you put your detectors at the end. So you get a spectrum like this. So this top one is the uniform spectrum without any defect. And these 4 lines are with these point defects. So you can make a filter like this. These are all the characteristics, what you see on the right side. This is a simulation. Not from the tool, but our own program. One of the student worked on this photonic band gap structures, and he has written his own FDTD programs, starting from the Maxwell's equations to put it in the MATLAB, and then you can solve it. Nowadays, you need not do that. That software does that. And it is easily available also. Even MATLAB programs are available now. You can just key in and then you can manipulate. You can change the refractive index or whatever parameters you want, grid size. All the things you can change for those who are doing research. So this is a 12-channel filter, the same idea, but they have manipulated, you have optimized, you have carefully choose various factors such that you get a very good filter characteristics. I'll show you that. You can see this comb filter characteristics. All the channels are uniformly distributed. Intensity is almost same. Okay. Of course, a lot of noise-like things are there outside the band. All the junk we are not so much interested. But you see the previous one, I'll show you just for example. See these 4 channels. They are not equally distributed, equal intensity. Then one more example. And study, a lot of studies we do with respect to dielectric constant, what happens, with respect to channel spacing, what happens, all those things you can combine. Then one more final topic called optical MEMS. You can say it's a combination of electrical, mechanical, and optical devices on the chip. It is possible to do mechanical components also on the chip by lithography, etching out, all the MEMS techniques, you can say. So this is a dramatic example. In about 1996 or so, people have demonstrated that you can make an optical bench on the silicon wafer. So what all we see on the physical table, they have made replicated onto a silicon wafer. This is a mirror. The flange can pop up or down and reflect the light. This is the application part. You can see there are an array of mirrors and inputs and outputs. Some of them are active, some of them are flat. So you can do any connectivity, whatever you want from this, by this mechanism. So a lot of optical MEMS people have done for networking applications, for biomedical applications, switching, and so on and so forth. So this is a summary of MEMS technology for optical application like diffractive optics and adaptive optics. Many things people have done. I think that much is enough for them. This is an example which we did in our lab, Another student worked on MEMS pressure sensor, optical MEMS pressure sensor. We have made an interferometer on the top of this wafer, and then below this arm, below one arm, etched out a diaphragm, thin diaphragm, about 50 microns or so, and then it can measure the pressure that is applied uniformly on top of it. When there is a uniform pressure, it will reflect in the form of a phase shift and intensity change. So this is the response characteristics for different modes. TETM modes are there, and what is the wavelength shift and so on. Typically about 100 microradians is the sensitivity. That's all I think. For timing, we'll conclude. I've taken slightly close to that time. So if for those who are interested, you can see the Nishiyara's book. And also there is we usually start with, there is one electro-optics handbook by Wayent. This has got several topics, several chapters. Each chapter is a topic, like fiber optic sensors, optical communication, like that. Chapter number 26 is the photonic optical integrated circuits by the same people. Nishiyara and these have a book. So the same people have written one book chapter. So within 30 pages, you can brush up or revise or get introduced to the subject of photonic integrated circuits. I've taken many of the pictures from that. I'll acknowledge the source. Then there are a lot of special issues of journals like JLT, Journal of Light Wave Technology, then special topics in quantum electronics. All these we have special issues every once in a while on not only integrated optics, non-linear optics, biomedical optics, optical signal processing. There are many issues. For those who are interested, should look at all these journals. Optical also has got very good special issues. In the beginning days, much of the material has come in Optica only. Nowadays, more and more, of course, Optica is more fundamental papers than IEEE. So, if you want more and more applications, you should look. And also, if you want to do optical communication or optical sensors, then this is very good to have this combination. I hope you will make use of all these things. Thank you very much for listening.